Today we're going to talk about linear functions versus exponential functions. Now, linear functions are something that you should already be familiar with. These are the functions that we have been working with all year. Linear functions are your constant rate of change with your slope and a y-intercept. So in this first part, can you think about what the formula is for the general equation of a linear function? So meaning not a specific slope or a y-intercept, but the variables that we use to represent those two items in a linear function. So take a minute, see if you can pause the video, fill in the equation, and then in the bottom, try to fill in the table. Once you have those things done, you can play the video and continue through. Okay, so the equation for a linear function is y equals mx plus b. The m represents the slope, and the b represents your y-intercept. So remember, the slope is your rise over run of a function, and your y-intercept is where the function crosses the y-axis. So now to get a table of values, what you're going to do is you're going to get your calculator, and in your calculator you're going to type in, press the y equals button, and then type in the 3x plus 2. So you need to put this part in your calculator. So pause the video if you need to, go to y equals. You want to be able to look at the table to make sure that your table matches the values that I am giving you. So in y equals, type in 3x plus 2. Then second graph will show you the table of values. Now the first thing we need to think about is a linear function. It's not restricted. The domain does not, they don't say anywhere you need to start the domain at a specific value and end at a specific value. And it's not a real life situation. So there's no reason to exclude negatives. So because of that, when we go to y equals, we don't actually, even though if I look down at the graph, I can see that it's just a plain grid here. And so it's not clear if we should use an L-shaped graph or if we need to use the 4 quadrants. So you have to think about it, since there's no reason to restrict it. This graph, originally being just a plain piece of graph paper basically, we actually need to draw in the x and the y-axis because there's no reason to not include negatives in the situation. So when we look here, I'm actually not going to start with the table. I'm going to go to my graph and I'm going to draw in my x and my y-axis. Remember to use a straight edge to do so. Okay, so now that I've drawn in, and you should pause the video if you need more time, draw in your x and your y-axis and label them with x and y. Now that I've done this, I can count back to see how many lines I have. So if we start here, at the middle is 0. I tried my best. Yours might be a little off, but I tried to make mine in the center. So if I go back, negative 1, 2, 3, 4, 5, 6, 7, that tells me that the smallest x value I can have would be a negative 7. When you go to y equals and you look at the negative 7, the number is too big. So we're not actually going to start at negative 7. So we need to go through, because the smallest y value I have here is negative 1, 2, 3, 4, 5, 6, 7. So anything bigger than or smaller than a negative 7 can't go on this graph. So we need to go through our table. So you need to move through the table to find the x value that is the first one that we can actually plot. So move through your table, try to write down what you think would be the first x and y. Pause the video if you need more time. So the smallest x value that I can plug in here is a negative 3. So for the x, I'm going to put negative 3. So in the table, we're actually going to show how the negative 3 is the x and the negative 7 is the y. Those are the end things that I put here. The x is negative 3 and the y is negative 7. In the middle, I'm actually showing how we sub in the y value and we sub in an x value here. So when we sub in x, the negative 3, we get out the y value, the negative 7. So in goes an x value, out comes a y value. And this shows that substitution, plugging my answers in place of the x and the y variables. But remember, the x is your input, the y is your output. Then we're just going to do this for the other points. So the other good points that I have once I start at negative 3 is going to be negative 3, and then negative 2, negative 1, 0, and 1. Then for the y's, I'm going to do the same thing. So remember, those are just from looking at the table in my calculator. The middle part is an added part. This is going to be a reference. I've added the substitution so you can see how we sub in x values and get out y values. Okay, so again, you might need to pause the video here to go ahead and write those all down, but we're just subbing in each of the values and showing how we get out the y values. So when I sub in the negative 2 in place of the x, I get out a negative 4, and then we sub in a negative 1, we get out negative 1, sub in 0, get out 2, sub in a 1, get out a 5. So that just shows me that these are all my points, my x and my y points, when I sub in using the equation. Now you can go to the graph and plot the points that we just found from our calculator and then verified by substituting in the x values. So I'm going to start by plotting negative 3, negative 7. So remember, start at the origin, go back 3 because that's an x value, and then down 7, and that's your first point. And then continue plotting your other points. Negative 2, negative 4. So we're going to go back 2, down 4. And then we're going to go negative 1, down 1, 0, up 2, and 1, up 5, plotting all those points. Then you need to get, remember, we need a straight edge again to connect the points. Once you've plotted all your points and you've connected with a straight edge, remember that we're going to put a label on there just because we're in that habit. When we had systems of equations, we had to label them because we had more than one thing on the graph. So just sticking with that same habit, always label what you just graphed. So y equals 3x plus 2 goes on there. And then now we can put arrows on the sides because, again, we're not restricting the domain at all. There's no reason to not include any given x values. It's not a real life situation. They didn't tell me that the domain is restricted. So I have my arrows so then I can go answer my domain and range questions. So domain, remember, are your x values. So we need to say what the furthest left and right the graph goes. So if I look back up at the graph, the furthest left it goes, I see an arrow, and the furthest right it goes is also an arrow. So that means that my domain is negative infinity, comma infinity. And then remember that infinities always get parentheses around them because we can't actually reach infinity. Now for the range, if again I move up and I look, the lowest it goes is negative infinity, and the highest it goes is infinity, again because of those arrows. So that means that my range is actually the same thing as my domain, negative infinity, comma infinity. Okay, so that whole part was all review. Our linear functions are something we've already been working with, but now we need to talk about exponential functions. So our exponential functions, the general form, and we did talk about this in class, but if you don't remember, it's okay. We've only talked about it once so far, but if you can think about what did you do, remember what the general form of the equation is for an exponential function? So the general form is y equals ab to the x power. And again, all of these things might be new to you. We only talked about it one time. A, we talked about as what moved the graph like up or down. It kind of changed where the y looked like, and we talked about what that meant. But when I talk about initial values, that's your A. So A represents your initial value. And that makes sense that that would also be your y-intercept because the initial value is really when no time has passed, so the x value would be a 0. So the initial value, if you want to write by the A that it's also going to be your y-intercept, that may be helpful. But you always hear me reference it as the initial value. And then your B value is the growth or decay. So we did talk about how the functions can either grow or decay, and that's all we know about them at this point. So this is going to be your growth or decay factor. That's what the B represents. So remember I talked about as soon as you see the x exponent, it's an exponential function, but we'll talk about ways to identify it using the growth or decay factor and words that are in there as well. if you know those pieces of the exponential function, it'll be easier to answer follow-up questions. So you really need to know the equation of an exponential function, y equals ab to the x power, and what the a and the b represent. If you know what those represent, it'll be easier to answer questions about exponential functions. Without knowing those pieces, it'll be very difficult to answer these questions. Okay, so now let's look at the graph of one of these. So again, we're going to go to y equals in our calculator. We're going to type in the 2 parentheses 3, close parentheses, caret, x. Remember that we need to put that x as an exponent, so we have to put it up as an exponent by hitting the caret, which is under the clear button in your calculator. Okay, so when you type that into y equals, we're going to do the same idea. So the first thing I'm going to do is actually move down and look at my graph and figure out, is there a reason not to include anything? So because it's not restricted, they didn't tell me that I need specific x values, I don't actually need the L-shaped graph. I can draw in the quadrants again. Now, there is something special about exponentials I touched on in class on Wednesday. We talked about how we had the x-axis where it gets really, really close to a certain value. In this case, if we looked at 2 times 3 to the x power, look at the graph, you'll see that it's the x-axis in this function. That's not always the case, but there is always going to be a y value that these functions get very, very close to, but don't actually touch for all the functions that we'll be working with. So they get really, really close to an y value, but they won't actually touch it. But for this case, we could try to figure what that one is, but we're just going to deal with the x and y axis to keep it similar. It's not an L shape. It's not restricted to only be the positive values. So I'm just going to go ahead and draw in the x and the y axis. So now drawing in my x and the y axis, that tells me that I can go to y equals and I can look at the table and I can identify negatives as my x's as well. Now when we look, as we go towards the negatives, we see these long decimals, or you might see possibly it rounds to the number 0 because your calculator can't expand out depending on how far you are on the x-axis and the x values. So when we look, the furthest that I can go on this graph is -7. So we could start at -7, but I see a lot of decimals in that area. So I'm actually going to go further up, like down on your table, to higher x values so I can see what happens to the y. Once I start seeing the numbers, I'm going to pause because I want to see some of those decimals because I need to know where did these graphs get really, really close to. So I do actually need a couple of those fractions, or in this case decimals, that we're going to turn into fractions in order to accurately graph the function. So when I look, I see at the x value of 0, I see the number 2 as the y value. So that's easier to plot. And then a 1 has a 6 and 2 has an 18. So that tells me that's the area that I want to graph. I'm going to actually start at an x value of -2, and I'm going to go up to an x value of 2, and then write down my y values. So as you see here, I wrote down the -2, the -1, the 0, 1, and 2. Now, when I go to my calculator for the first one, it doesn't come out nice. So instead of writing down that long decimal, I'm going to just show the substitution, and I'm going to go to the regular screen of the calculator to type in the number. So then once I get the long decimal, I can hit math, frac, enter to turn it back into a fraction, which will be a better answer that I can actually use. So while I was writing down all the subbing in, I subbed in each of the values and showed that in the middle for each x value input, plugging in the -2, -1, 0, 1, and 2. Then from the calculator, you'll get the y values, which I can then put on the other side of the equal sign. Remember, for these first two, we get long icky decimals in the table, so we need to go to our regular screen to type in 2 parentheses 3, close parentheses, and then caret, underneath the clear button, -2. When you hit enter, you'll get a long decimal again, but then when you go to the calculator and you hit math, frac, enter, it'll put it back as a fraction that we'll write down for the y value. Okay, so now that I have my y values, 2/9, 2/3, 2, 6, and 18, again, just getting those from the table, and these two, getting them on the regular screen, math fracking to get 2/9 and 2/3. Now we can go ahead and plot these points, so x, comma, y, plot each of the points, and then we'll connect, but pause after you have graphed all of those points. Now remember the 2/9, that might be a little harder to graph if we think about it it's going to be lower, closer to 0 compared to 2/3. So there's a couple important things when you graph exponential functions. You need to use a smooth curve. So notice that I did not use a straight edge. These show that they are curving. Exponential functions have a curve. When you go to the graph, you will see that. So the curve in between is not usually hard, but I have a lot of kids that have trouble with the end behavior. So this one, when we go, this gets really close to the x-axis in this case, to a y value of 0, but it doesn't actually touch it. To show that, you need to make sure that you stop your line before and leave that little bit of white space and then just put an arrow. I don't even usually try to extend past because I don't want to try to keep it above the x-axis for longer than I have to. That would be harder to do. So I usually just do a little bit and then put my arrow. Same thing for the top. You want to just show that it's going to continue out a little bit, but I don't go far past the last point that I was able to plot. Errors that I see, which you do not need to write down, but I just want to go over them, is that when kids get to the end, sometimes they'll curve in like this. That would lose points. Any kind of curve going in. Additionally, going straight up, vertical up, would give you a lost point because it doesn't go vertical. That would make it not a function. The other thing is actually showing it touching that, in this case, x-axis or whatever the asymptote is, and that does not happen, so that would lose points. Even worse than that is when kids go past that and pretend it goes further down than it actually does. That will definitely lose you a point. So you need to be very careful with the end behaviors. That's why I usually keep them close to the last points that I was able to plot. And then the arrows just show me that it would continue in that similar pattern. The next thing that we need to do is just throw a label on this graph to show that it is the function that we were given. Okay, so for the domain, remember, is your x values. If I look at this graph, I can see that there's an arrow showing that the x's will continue going left forever. So my furthest left would actually be a negative infinity, and the furthest right, again, even though it's going very steep up, it is still going out a little bit, so it's going to go right forever as well. It's going to go very steep, but it will still continue going to the right. So my domain is, again, negative infinity, comma infinity. Now, the range takes into account that fact that it gets really, really close to a value but doesn't touch. So when we look for the range talks about the y values. So when we look for the range in the graph, I'm looking for the lowest it goes. Now, the lowest it goes is important because we talked about how these functions get really, really close to a specific y value, but they don't actually equal it, and they will not cross it. So we talked about that concept of exponential functions. So in this case, they get really, really close to the x-axis. If we look at the graph on the calculator, it might even look like it touches the x-axis. Now I'm telling you it gets really, really close, and your calculator will even eventually round, but it does not actually touch that asymptote. So in this case, it's getting really, really close to 0, but does not touch it. Think to yourself, how do we show that it gets really close, but does not equal it? Well, we need to use a parenthesis around it to show that. So it goes from 0 with a parenthesis to show it gets really close. And then when we look at the top, it goes up forever. So that tells us that my range is going to go to infinity, up forever. So starting at 0 to infinity, and remember it's not including that 0. Okay, let's flip over to the back page. This back page is all just for your information. So there's no questions on here. It's just a lot of information that I'm going to go through with you. So we have linear versus exponential review functions. So this is just kind of, it says review session 1 because this is all review information that we'll be able to revisit later. So this piece of paper is going to be very important. We don't want to lose this. This has a lot of valuable information on the front and the back of this page. So we're going to keep this in a safe spot. So we have, it's called linear function. The equation general form is y equals mx plus b. And then we have the exponential function, y equals ab to the x power. And those are where the a and the b and the m and the b that we talked about on the previous page, what those represent. So parent function, that's just your most basic. We'll talk more about that in our last unit, but this is just the most basic. So just plain old f of x equals x, where the slope is 1 and the y-intercept is 0. So that's your parent function here. And then we have just an exponential function here. So when we talk about domain, remember we talked about this on the previous page, what the domain is, a different representation of it, and then what the range is for those. Key features for a linear function, it has a constant rate of change, something where it's like a slope where we go up and over by the same amount every time. That's a constant rate of change. Common average rate of change. We talked about all those things. Constant growth factor, that means that it's multiplying by the same thing all the way through. So for slope, we have it when it's increasing, so positive slope, a negative slope when it's decreasing, horizontal lines, so they have the slope of 0, and vertical where it's an undefined. And these functions have your y-intercept, which could also be considered as your initial value. Again, it's kind of when no time has passed. That's represented with your b. Now for the exponential functions, they can either grow if the b value is greater than 1, or decay if it's between 0 and 1. We'll talk more about growth and decay later, but those are key things that you'll need to know. They also have a y-intercept, which we will call an initial value, but in this case it's represented by the a value. And they have that asymptote like we talked about. Then we have tables. When we look at the tables, when we talk about a linear function, we have this. Now this is going, if you go from -2 to 0, that's +2, 0 to 2 is +2, 2 to 4 is +2, 4 to 6 is +2. So that's a constant adding each time, just like the y value is. 4 to 10 is +6, +6 to get to 16, +6 to 22, +6 to 28. So this shows a common difference where we add by the same thing each time. Now if we look at the table for the exponential functions, these are going up by 1, so 0 to 1, 2, 3, 4. But the 2's, if we tried to do that same idea of finding a common difference, 2 plus 4 is 6, 6 plus 4 is 10. So that doesn't hold true. So then I have to go back, well, let's try multiplication. 2 times 3 is 6. 6 times 3 is 18. 18 times 3 is 54. 54 times 3 is 162. So this follows through with a common ratio, multiplying by the same thing each time. Real world scenarios. You will see questions like these where they try to have you identify if it's a common ratio or common difference. So in this case, we're going to talk about linear and exponential functions. So on the left here, we have this amount of money in a savings account where $150 is deducted every month. So if you think about that, that means we're subtracting 150, subtracting 150, every month subtracting 150. That's the same amount being taken out. Similar idea here, the amount of money in a piggy bank, $10 added each week. So we're just plus 10, plus 10, plus 10, but it's the same idea. A monthly phone bill has a flat rate of 50 per month plus 2 cents per minute. So we're adding the 2 cents for every minute, plus 0.2 plus 0.2, plus 2 cents, plus 2 cents, plus 2 cents. A taxi charges $3 plus an additional 25 cents per mile. So again, 25 cents for every mile, 25 cents, 25 cents, 25 cents, and so on. The catering company charges a service fee of $500 plus an additional 35 per guest. So we're adding the 35 every single time. So those all have something added each time. What's different with your exponential, and I'm going to highlight some words in here because this is new for us. A population of beetles is increasing at a steady rate of 6% per week. So when we see that rate and the percent, that is our clue that it's an exponential. A saving account has an initial value of 720 and a 2.5 interest rate per year. So again, we're multiplying by that 2.5%. A cup of coffee is cooling down, so its temp decreases at a constant rate of 8%. So again, those keywords there. The number of mice in a scientist's experiment doubles each year. So looking for words like doubles, triples, is half, anything like that where we have a multiplication happening. And the last one, $14,000 is initially invested at an interest rate of 3.5% compounded monthly. So again, we have that rate and the percent. Those are our clues that this is talking about an exponential function. Okay, so we'll talk about this more, but these are all just key information that you'll need to know for linear versus exponential functions. Have a great night.